Hello everyone, welcome you to our technological session on transforming the tooling industry with advanced additive manufacturing solutions in collaboration with Phillips Additive and EOS. My name is Darshna and I'm the Associate Editor of OEM Update magazine. I would like to introduce the theme of our technological session first. The tooling industry globally is the fifth largest horizontal industry that sustains every vertical in manufacturing sector. Increasing challenges in the tooling industry, like cost, customization, and skilled labor, have motivated tool makers to constantly innovate to stay competitive. And additive manufacturing is the answer to that. In additive manufacturing, the material is applied layer by layer in precise geometric shapes based on predefined model. It offers unparalleled advantages such as complex production capabilities, low cost customization, and rapid turnarounds. Today we have with us Mr. Jayesh Rathod, who is a Senior General Manager and Head Engineering of Tooling, Godrej and Boyce Manufacturing Company Limited. Mr. Michael Jan Galba, Principal Engineer, Advanced Metal Solutions at EOS, and Mr. Joe Ajay, Business Development Manager EOS, along with Samarth Deshpande, Application Engineer from Phillips Machine Tools, to discuss additive manufacturing as a solution. OEM Update has partnered with Phillips Additive in collaboration with EOS to discuss a wide range of AM solutions and address the diverse needs of the industry. Phillips Machine Tools is one of the one-stop solutions for metal cutting, forming, and additive manufacturing. And it is trusted globally by the manufacturing industry. And Phillips, along with EOS, enables customers to produce innovative and high-quality products based on industrial 3D printing technologies. EOS is global technology and quality leader for high-end solutions in the field of additive manufacturing. It was founded in 1989, and they are pioneer and world leader in the field of direct metal laser sintering. And they provide a highly productive additive manufacturing systems for plastic materials. Before we start, let me explain the sequence of today's event. We will begin with individual submissions, wherein our guest speakers will present their talks on the respective topics, followed by a Q&A session. We have a chat feature available for you to communicate with our panelists. So if you have any questions or thoughts, feel free to share them in Q&A box. So let us begin with our technological session on transforming the tooling industry with additive manufacturing solutions. First up, we have Mr. Joe Ajay. He's a business development manager at EOS, specializing in additive manufacturing, a Lean Six Sigma Black Belt professional and certified reliability engineer. He has been recognized by the Indian Air Force for pioneering India's first metal 3D printed flying part and by the Indian Navy for successfully implementing additive manufacturing in naval ships. He actively contributes to AM standardization. Today, Mr. Ajay will talk about additive manufacturing solutions for tooling industry. So you can start with your presentation.
Thank you, Darshana. And please let me know if you can see my screen. Can you see my screen?
Yes.
Right. So, evening, everyone, and I'm glad that you have set aside some time to hear from us. And for today's session, I have three topics to address. Number one, who EOS is. Number two, what solutions that we offer, and some success stories from our customer. So just 3 points. And as Darshana also mentioned, we started our journey in 1989. And since then, our bread and butter is just additive manufacturing. We build additive manufacturing machines. We process or we qualify raw materials. We are not a mining company, but we process materials that make it suitable for additive manufacturing. We have both metal and polymer solutions as just one stop. And so we have in market roughly about more than 4,500 machines globally running. And I'm very proud to say that we were the first one to commercialize metal 3D printing for the entire world. So that is a set record. I don't think anybody can break it. So if you ask us what solutions that we offer, let's say you have a digital device, a product that is designed, and if you want to realize it, the end-to-end solution is what that we offer. Want to have the part being built in additive manufacturing machine? Yes. And have the set of alloys to be the definitive alloy grades that you wanted? Yes, we do have some offerings from our bucket. And the most intelligent or the price position from us is how the laser and materials interact, and that we call it as the process parameter, and sizable quantities of process parameters that we have for different grades of alloys. As for the CAD or simulation purpose, we have some partners working such as Dassault Systems, NX, so on and so forth. And on the post-processing, such as smoothing, microplasting, machining, and Phillips is also one of our partner who can take care of the finishing operations for you. So additive manufacturing, as you know, I mean, it's been quite some time in this industry. There are multiple different technologies, and at EOS, we work on laser powder bed fusion. The raw material is in the form of powder. We spread the powder over a platform, and we use lasers to melt, and layer by layer, we build the product. As simple as that. Sounds simple, but very complex engineering is involved. So for die casting industry, as today's theme revolves around tooling, so when we talk to some of our prospects in the first primary interviews that we took, they said if there is a product and if you want to realize a product much before it goes into mass volume, the first step is, of course, quick protos, where the product is either machined with a 6061 aluminum or sandcasted with ALSA 7 mg. And at EOS, we have a similar grade of alloys, a variant of LSA 7 mg called F357, A360, and ADC10, A380. And once the product forms are realized and then fit finishes verified, then goes into pilot production stage where you have some soft tool being done, whether in P20 steel or any other quick tool, a cheap tool that can make a quick die-cast parts for 50 to 100 numbers, again with ADC grade of alloys possible. But today, with EOS, we have a very high productive processes for aluminum alloys, A360, and all the set of grade of alloys, where you can eliminate this complete process with the same set of properties that you have for the end-use die-casted parts. And for mass production, when the volumes run into, let's say, 100,000 parts or about 1 million parts, then we offer tools, or we have processes that work on tool materials where we can have, just with our creative mind, we can offer complex cooling channels with the benefit of layer by layer building. And of course, that is the conformal cooling technology. And for plastic industry, similar approach, quick proto, pilot production, and mass production. For quick protos, they take a block and then machine it, plastic parts machined, or if not, a material is extruded just like the toothpaste kind of technology. And whereas at EOS, we offer SLS process where there is no superstructures at all. So just print the part, de-dust it, and then you have a part in hand where you can directly use it. And when it has to be in few hundred numbers, then people go for vacuum casting, where you make a soft tool and then followed by you pour you mix the you mix the polymer, blend it, and then pour it into tool. But in SLS, we can stack the parts in Z-axis as well. So quick parts without any superstructures, without any wastages, quick turnaround time we offer. And for mass production, we make use of the tooling performance, tooling process parameters. Thereby, we could offer conformal cooling circuits or conformal cooling technology for plastic molds as well. So direct parts, many times when we talk to people, they ask us how is additive manufacturing performances when we compare to die-casted parts or when we compare it with rod parts, so on and so forth. I think the standard speaks for themselves. So when we compare with some of the industry standards, such as GIS standards, we saw LSA 7 mg, which is the F357 grade. It's direct and overlap of these properties. You can see whether it is sand casted, whether it is permanent mold casted, or loss wax method. Even with that, the properties overlap. There is little bit of increase in ductility that by nature comes with the microstructure, which is inherent to the process. And ALSA 10 mg, again with the same standard 5202, overlapping of these properties. And recently also A380, ADC10. I think this is one of the very common alloys in die-cast industry where you can have the same part which is going in for mass production being printed and achieve the same property. So the delta between the proto and the end-use parts is reduced with additive manufacturing, and thereby you have a quick turnaround time as well. So on pilot production, this is one case which I'm very happy to present. It is done by one of our customer MXC, and this is for a lawnmower, a small engine casing, which is an air-cooled engine casing. And you can see from the image that the engine casing is highly nested, right? And the total count of parts is 36 parts. And surprisingly, this is done in 2 days' time, right? Or less than 2 days' time. 36 hours is the print time. And if you compare 1 hour per part is what the exact number is. And okay, we have the benefit of time. Now comes the economics, right? Here is the value, including the material and post-processing, roughly about 80 or little above 80 euros per piece. I don't think anybody in market that could meet this number. The technology is so mature that you can use not just for protos, but you can also replace the pilot production series jobs with additive manufacturing today. On polymer, we predominantly work with polyamides and TPE and various polyamides, nylon 11, nylon 12. We have the flame retardancy. We have the carbon film material for better flexural strength, glass film materials for better temperature resistance, so on and so forth. And TPU, under TPE umbrella, we have a fair bit of percentage elongation where you can stretch and use it for your bushings, so on and so forth. And if you want any specific or requirements, we can talk later after this session. So when we compare the properties with VDA standard for additive manufacturing, our processes and the standards matching. Unlike what we see in metal, where we have process-based standards, in polymers we have product-based standards. So we have to compare with products, but fortunate enough that we have VDA standard for additive manufacturing, and that says the properties that shows clearly our properties such as PA2200 overlap with PA12, and PA11 properties which were set by the industry standard, PA110 matches, so on and so forth. So this is the production case similar to what you saw on engine casing. Let's say this is a product joystick. We use it for gaming consoles or an off-road vehicles, so on and so forth. So this part, if it has to be printed in a small series, such as 36 parts or a little lower than that or a little higher than that, about 50 parts or so, we can print 45 of such parts in one full job, and that takes roughly about 2 days of time. That quick is what our process is. And if you compare injection molding, the economics is way higher. I mean, it doesn't match at all. We are talking somewhere around 45 euros per part, but if you see injection molding cost about 0.7 euro per part, right? It doesn't match at all. But here is the breakup. For 100 parts, your tooling cost is way higher, right? It's not even a match. But let's say if we go in bigger volume numbers, then we can meet, we can see the economics come into play, that injection molding is far better, cheaper when we have the large volumes. But where exactly is the break even? We found out that for this particular part is roughly about 800 pieces. So this is geometry to geometry, and we can work on few cases to understand where exactly we have the break even when we compare with injection molding to direct parts with SLS process. So the need for AM tools, coming to the theme of the day, tools, right? So for die casting, this is an interesting survey done by NATCA, the North American Die Caster Association. They say the problems faced by die casters, the number one problem is porosity. Gas porosity, shrinkage porosity, blisters, and whatnot. Everything put together contributes about 35% of their defects, product defects, followed by all other issues, cracks, your solders on tool, flash, so on and so forth, erosion of the tool, right? And then you have supply quality coming in, the dimensions, CPK values, so on and so forth. And then finally, the least amount of headache is on tool cost, right? And interestingly, if we read through the Natka's book on E5 I guess they say roughly about 50% of all these defects can be resolved if we have the right tool temperature. More than 50% of these defects. And in plastics, the game is a little bit different. We had an assessment along with one of our partners for a cup such as this. And they say in terms of productivity, if we have to increase the volume numbers, because plastics parts go in many numbers than die-casted parts, they say the biggest contributor for the non-value add time is the cooling time, right? So if we have a quick turnaround time or quick cooling time, then we can have a better ROI for our tool. So the solution is, of course, temperature optimization or the thermal control, which is offered by conformal cooling. And the benefit with additive manufacturing is because we do layer by layer, we can achieve whatever shapes that we want. Of course, we play within certain design rules, which by nature for any other manufacturing process is inherent, right? So people ask us often, how at all if I have to go about conformal cooling circuit, if I have to design it, we have three abstract rules. Of course, we have to go case to case basis, but upfront, in a nutshell, if we have to put in, easily follow the contour of the part and keep a safe distance from the tool surface, followed by we don't have sharp edges where of course we have enough cleaning issues with the existing channels. We don't want to have the cleaning issues again with conformal cooling, right? So let's not have the blind corners or sharp edges thereby where we can have where there could be an issue of clogging or some sort of scaling coming in. Let's not have that. And finally, let's not have too many branches where we would have pressure losses, but then have limited branches, but larger part profiles. I mean, the channel profiles, thereby we could have better heat removal. So that being said, we have a few tool steel processes with us. Number one is, of course, the popular Maraging steel 1.2709, followed by we have H11 also. We have CM55, which is cold work tool steel. Also, we have tried it with die-casted, works well. And we have Corax for plastic molds. And if we compare the productivity, we roughly somewhere have 100 grams per hour for almost all these materials together. So which means if you have certain few kgs of parts that is to be done in a year, you can understand how much of utilization that you have for additive manufacturing machine. So a few stories for inspiration. I like this story very much because this is a very high volume part. Automotive compressor housing that was done by Toyota along with one of our customer entity data in Japan. And they had this issue of soldering of tools, right? Aluminum sticks to the tool and then, they have to polish it. There is a downtime to it, so on and so forth. So they tried with deep cooling channels, as you can see in the first image. And then they tried it with quick preventive maintenance, so on and so forth. But all this could reduce to 50% or so. Good progress, actually speaking. Now, if you have conformal cooling, they even tried, as you saw earlier, also the different cooling um, design guidelines. They tried thin channels, they tried thick channels, so on and so forth. And you could see with the designed conformal cooling, they had zero soldering. From 50% onwards, they have actually come up with no more soldering. The tool doesn't stop for soldering sake, no more polishing, right? So a few more examples from some of our customers. Transmissions, bushings could reduce the cycle time, steering columns, reduce the defects. And people always ask us if we have H13 tool steel. Okay, we say the answer is doesn't matter what material that you put in. Of course, you need to have the material that is suitable for hot environment. But if you have conformal cooling and if you have enough strength in the material, I think you can go ahead with overperforming or outperforming H13 as well. So this is my last success story from injection molding. This is one part used for some of the cosmetic applications, and they had the issue of having wobbling temperature going up and down, at the injection point, which effectively carried over to the part, having gas pores and so on and so forth, warpage and whatnot. Every defect that you could see has an issue when you do not have the right temperature of entry for plastics. Now, in order to reduce cost, what we have done is we have taken a preformed maraging steel, 1.2709 steel, machined it, and then made it suitable such as what you see here, so that the drills are just straight drills, right? And after that, when you have the profile, you just build on only the profile where you need the conformal cooling circuit. And that's what we did it. So from 18 seconds, the cooling time or the cycle time has come down to 8 seconds. That's a benefit of it. And due to the hybrid manufacturing, where we have the half pre-machined block and then printed block, we could reduce cost. And even with the tool setup time or the machine setup time, we had some of the unique tools in our machine where you could have quick positioning, and with that we could have the turnaround time or the print time also being reduced. And today we could achieve more than 3 million shots with this tool. So that's about it. And so for takeaway, I would like to leave with 3 points. At first, we offer something beyond proto, right? Additive manufacturing is not just proto parts, but we offer a bridge between proto and mass production. And even with that pilot production parts, we offer the same or similar properties to what you get it in the end-use die-casted parts or end-use injection molded parts, as you saw from the standards. And finally, with AM tools, you have a better tool life, you have reduced defects, and you can increase your productivity. So that's about it. And I believe we can take up questions at the last, Darshana.
Yes, sir. Thank you so much for setting up the ground for additive manufacturing and how it benefits tooling industries. If anyone have
Thank
any
you so much.
questions for Mr. Joe, please put them in Q&A box. We also have a poll.
Okay, now I see there is a question that maybe we can address all the questions at the end of the session. Yeah.
Correct. Yes.
Okay.
Joy, can you see the poll results? You can, right?
Yes, we can.
Yeah. Joy, can we end the poll? Yeah. Thank you.
Next, we have Mr. Michael Jankalba, who is the principal engineer. So should we stop this poll?
Yeah.
Okay.
Please go ahead.
Thank you. I will be sharing my screen now. Hope you can see it.
Next, we have Mr. Michael Jankalba, who is the principal engineer of Advanced Metal Solutions at EOS. Michael Jankalba is specializing in state-of-art additive manufacturing solutions. With a customer-centric approach, he translates industry needs into groundbreaking technologies, embracing co-creation to drive innovation. Passionate about pushing boundaries, he collaborates closely with customers as equal partners, turning their application into future-ready solutions. Today, Mr. Galba will be talking about the state-of-art AM tech solutions.
Thank you so much for having me. I'm, as mentioned by Darshana, Michael Garber from the US. I've been in the industry since 16 years now, mostly or solely focusing on metal additive manufacturing. And I'm really passionate about technology in general. So tooling is one of the cornerstones of additive manufacturing, and I think it's also one of the initial ideas to go into tooling with certain materials. I will be talking
Sir,
about...
I want to interrupt you a minute. Mr. Galba, I want to interrupt
Yes.
you a minute. I
Yes.
would like to inform everyone who is attending in this session, if you are facing any difficulty to follow the pronunciation, you can click on the CC button on the toolbar, that is captions. So you can see what he speaks comes in the caption there. So it will make, you can understand very well what he speaks, and it will come on your screen as well. Thank you, sir. Sorry to interrupt you. Mr. Galba, please continue.
No problem, no problem. Thank you for giving the attendees the possibility to make use of this function. As mentioned, tooling has been a cornerstone of additive manufacturing at EOS from the very beginning. As a matter of fact, one of the first applications were in tooling. Tooling has, over the especially past periods, seen a lot of ups and downs and had been relatively quiet in the past due to the most dominant reason that the tooling itself or manufacturing of the tools was very cumbersome and slow processing. And this is something where we will show with new technologies of how we've overcome this. Share my screen. Switch to the next slide. On the left-hand side, you can see the process of M290 system processing MS1 material, and you can see that the deposition rate of that material is rather slow. So if you think about really big and massive components, in the past, the processing times was always very, very long. This ultimately led to really high cost in additive manufacturing, whether it was either in the tool itself or in additive manufactured parts. With new technological advancements, the processing speed was really overcome dramatically. So we have mastered with new exposure parameters the energy input and the interaction between the powder and the laser source in a way that we can, on our latest machine generations, produce over 1 kilogram of material per hour. So looking back, I mean, yes, the tool costs were predominantly defined by the processing time inside our equipment. I think today we see, and I will also show this a little bit later on the application samples, that the main cost driver is not really the productivity anymore, it is really the material and the availability of the right materials for a specific application. Here, one quick example. This is our state-of-the-art M300 systems. It is equipped with 4 times 1 kilowatt laser systems, and we are able to really deliver 4 times 1 kilowatt in a relatively small process chamber. So the process chamber has only 300 by 300 by 400 millimeter in that height. And having 4 kilowatt of light power inside such a enclosed encounter is putting a lot of stress onto the entire system itself. The entire system architecture, however, is prepared for it. So we have demonstrated now with aluminum as well as with other materials that we can easily handle that. So this is setting us apart, realizing part geometries in production speeds that have been unmatched as before. I brought with you here a small electronic housing in the range of about 50 grams. Manufactured in ALSI 10mg. ALSI 10mg as a placeholder for, let's say, the standard common aluminum alloys. So whether you're using ALSI 10mg or ALSI 9CO3, the productivities are pretty much the same that you can achieve on those systems or in similar ranges. To put that into perspective, what does it mean cost-wise, where we come from on the M290 system? You could, like with an undiscounted system price, with an undiscounted material, so we're talking all about list price, depreciation period of about 5 years or 7 years in this case, 6,500 laser hours as utilization. the cost per part was in the range of 66 euros and 70 cents additively manufactured. The way forward was then to develop new process parameters and also go into higher layer thicknesses. So on the M300 with the 400 watt laser system, we were able to drop that cost already dramatically down. With the M300 4x1 kilowatt system, ultimately, we were able to cut down the cost really, really dramatically. Now, interestingly, is producing over 240 parts in a stacked configuration in less than or in about a day's time is really something that is enormous. I mean, I've come from a period of time where printing aluminum parts was always in the range of a few days, and if you have a full platform, you were waiting for almost a week until the part can be unpacked. And today, this is, I think, to me personally, as close as to a replicator technology from Star Trek that you can get. So part times for 6 minutes or 3 minutes have become really relevant. But this is not the end yet. We have been at EOS always constantly pushing the boundaries of what is possible. And from the very early days, we thought we don't want to really join in the laser race. So who has a machine with the most possible scan heads on its system as possible? We don't believe this is the smartest way forward. Just as a matter of fact, the laser scanner optic components are amongst the most expensive and most sensitive components in an additive manufacturing machine. So by putting 8 lasers or 20 lasers or 30 lasers into a system, you are only increasing the complexity. We at EOS believe that there's other means to increase the productivity even further by not adding more lasers, but adding different beam shapes. We also strongly believe that you need dedicated and specific tools to solve a specific problem. As an analogy, for instance, if you have a broken car and you bring your car to a dealer to get your car fixed, the dealer has a lot of different tools that he can use to fix the problem on your car. In additive manufacturing, the tool of choice was always a hammer. Whether it's a 400 watt hammer, a 1 kilowatt hammer, or 2 kilowatt hammer, but a hammer stays a hammer. It's not the optimized solution or tool to fix a specific problem. With EOS, we have always the ambition to develop technology that is groundbreaking, and we've developed technology that can change an incoming Gauss beam into any arbitrary beam shape that we like. So we've ran various experiments on these systems with different beam shapes, and we've tried to optimize the energy inputs by not only putting more lasers onto a system, but really changing the energy input, so to say, the tool of choice that we're using for a specific material. What you can see here is a peek into our R&D lab, where you see such a system. It's a scientific machine with a high-speed recording camera here that can take up to 2,000 pictures per second of a small envelope, and that teaches us of how the energy source interacts with the powder. So what's brought here is an experiment that we've conducted quite a while ago. It has been also published in LinkedIn already, I think it's 3 years ago, where we have demonstrated that we do heat conduction welding at really high scan speeds with 1 millimeter spot diameters. So typically in additive manufacturing, if you want to melt metal, you use 80 micron or 100 micron Gauss beam. That means for 1 millimeter width to scan, you need about 10 individual scan lines to be drawn into the powder bed. With this technology, we've been able to increase the productivity by a factor of about 8 to 10 by not scanning 10 individual scan lines, but just 1. Charmingly as well is that this heat conduction welding process does not emit any side products. So what you see here is just a very, very clean melting of the material and not a laser welding where you have these spatters flying all around, causing disturbances in the process. here we've tried different beam shapes and how they interact with the powder, and all again showing a very different melting behavior. I don't want to go now too deep into the physics. What you see here is just keep in mind that the different beam shapes have a significant impact of how we can actually melt the material together. But I mean, you can. This is research, and nice and good that you're doing that. But you need to, of course, also apply it to technologies. And therefore, one of the first systems where we have applied beam shaping was with our partner Enlight together to equip M290 system with a 1.2 kilowatt AFX laser of the company Enlight. That laser provides you a possibility to change like within milliseconds from a Gauss beam into a, for instance, ring mode, a multi-mode laser profile. We've additionally also equipped our M300 system with the latest scanner technology, as well as with 4 times 1.5 kilowatt laser energy, and we have just unleashed like 6 kilowatt of light into a very small process chamber. The results are very, very impressive, because when we go to the applications, you can see on the right-hand side, so this is a quad laser system, but just for demonstrational purposes, you can see that on the right-hand side, this one laser here is producing with a conventional 80 micron Gauss beam, and one laser out of those 4 is using the full 1.2 or 1.3 kilowatts in this case, in Inconel 718 is a high performance super alloy. A significant higher amount of material to be molten, and also at the same time better quality. So when I initially showed that there's less process spatters and less process side products being emitted, here you can see that after a while, I will just forward the video. The Gauss beam is still operational, whilst the Enlight AFX laser is already done with all the melting. Just look at the surface, top surface of the melt. It's completely clean. There's no debris, there's no spatter in the powder bed. There's no overmolten particles being deposited that can alter your product quality. Also, recoating is a lot smoother in the beam shape process. And here, clear application of where we have printed with 4 times 1.3 kilowatts process parameters. You see the layer time has become really short. It's a huge part that has been printed, and yeah. Another application where I want to show is one car part with our partner Danfoss, and that has a stainless steel component as a conventional legacy design. So this part subtractively was being just cut from bar stock material, being drilled and threaded. And here we, with optimization, we can even today with the existing design match with a superior material to stainless steel the part production cost, which is really interesting. In the conversation with the customer told us that the design itself is 30 years old and has a lot of room for improvement, and there's a lot of additional mass in this object, and that is basically just coming from the fact that removing mass from the existing design was adding cost, whereas in additive manufacturing, the more mass you are producing, the more expensive the part is getting. So we are working with the customer to optimize the design, to reduce the mass where possible, and by doing so, we're able to also improve the performance of the component by the internal geometries and cavities. So reverse engineers, we have simulated the passage through this rotary piston pump component. So we were able to reduce the mass. We were able to, with the customer together, make a part that is better than today in a superior material for less cost than traditional manufacturing. Again, here, it was displayed this year on Fornext, this component. So we can produce these components in about or 4 kilos in a little bit over a day. So that's it's a really high fill factor. There is really a stress test of the system whether it can digest so much power. But I think application itself talks for it. Now, do we have that already available for the tool steel? Unfortunately not, but we are working on it. So tool steels are on our agenda because the tool steels have a lot of mass and they require significant shorter processing times. So this is something that we will be considering and looking into the near future. Now I want to bring you with another application example of our partner Husqvarna that were so kind and have demonstrated us with a challenging part. So here you can see where did we come from. From the past on the M290 system with a legacy process in 2011. This was clearly prototyping. So you were able to produce 4 parts in something over 2 days, and the part price, the resulting part price, was in a range where we are so far away from conventional or traditional manufacturing that the application never really made sense. We've asked the customer, can you design, modify the design to make it better for additive manufacturing, integrate functional integration, topology optimization, and whatnot? And they said, we are so far away from a target application price of about 20 to 40 euros for these chainsaws that it does not make sense for us economically to even waste a minute of our engineers' time to optimize for additive manufacturing, because it will never go at this price into an additive manufacturing realm. We said, okay, it's fine. We continued the development of the technology, and we have started, as my colleague Joey has demonstrated, in the past with the 80-micron processes, that we can manufacture those components in a stacked manner for about 80, 90 euros per component, or respectively around 120, 130 euros per kilogram. In this region, we were already closer to the manufacturing cost of the die-cast component. And the customer got really interested in working with us together on how to optimize this even further. So instead of like now saying, yeah, the little chainsaw for the little Michael Galbert who do his gardening work, and this future will be electric. So those millions of parts of those die-cast parts, they will eventually not be required anymore. But there's applications where professional woodworkers are carrying a chainsaw 8, 10, 12 hours through forest and are cutting down trees. For them, performance really matters. And those components, they can be also a little bit more expensive, but also optimized for weight, optimized for performance. And this is what we've demonstrated with Husqvarna, with the M4 Next, it's a machine that we are currently developing, that is coming into the market for this year's Fall Next, where we've again dropped the part cost quite dramatically, and also the productivity of part. And now looking also with beam shaping technologies in this, we can reach part prices that are comparable to real die-cast aluminum parts in the range of, let's say, 8 to maybe 10,000 components per year. So coming from over 500 euros per kilogram down to about 100 euros per kilogram is, I think, some very dramatic achievement. However, keep in mind, this is all list price of the system, list price of the powder, list price of the services associated with it. I want to also demonstrate how big the influence of the powder price is to the specific part price. And we'll quickly see that the powder price of, let's say, between 50 and 45 euros as list price for the aluminum is really dominating factor to the part price itself. So as a matter of fact, the machine time, if you have such high productivities, does not play such an important role anymore. Same with the machine utilization. I mean, the utilization of the system is becoming higher and higher. Today, typically, in a prototyping environment, you have machine utilizations of only a few thousand laser hours per year. In a real production scenario, you have to consider utilizations of the system of over 6,500, 7,000 laser hours. They are industry standard. And those have a really dominant effect as well on the part cost and with the system productivity. So through process innovations, we are able to deliver more and more power into the process chamber. And we believe that a system's performance increase of 50 to 60% in the near future can become realistic. And now going back again to this innovation today, towards the future calculational scenario, we can, like, just by considering an increase in productivity of about 20%, a reduce of powder price by about 30% and a high utilization, you can really dramatically bring the part price down into regions where really additive manufacturing of the final part starts to make great sense. And with that, I want to conclude my presentation. Please, if you have any questions, let me know, and I'd be happy to answer all of those. Thank you for having me here. Darshana, we cannot hear you.
Thank you, Mr. Galva, for sharing your insights on cutting-edge AM solutions. We have polling questions. Hello.
Here it is now. How does Gaussian beam differ from a top hat beam in terms of application performance, and how does the beam shaping influence the quality of the output? Okay. Shall we answer the question right now, or shall we answer it later?
Raised questions to be shared after the presentation.
Okay. Good.
Okay, we are closing the polling now. Okay. Thank you. Please go ahead, Darshan.
Next, we have Mr. Jayesh Kumar Rathod, who is the Senior General Manager and Head of Engineering of Tooling at Godrej and Boris Manufacturing Company Limited. He comes with 38 years of expertise in die casting and plastic mold design. Trained in die casting by world-renowned experts from Japan, he has set benchmarks in large and complex die casting dies for the auto industry. He has led successful projects for major MNCs like HMSI, Yamaha, Hero, and Mahindra, earning recognition as a top tooling supplier. Today, Mr. Rathod will tell us about the role of AM in reducing cost in high-pressure die casting applications.
Sir, please unmute. Jayesh, sir. Sir, you are on mute. Yeah.
Yeah. So good evening, everyone. I'm Jayesh Rathod. I'm heading die casting dies at Tooling SBU of Godrej Enterprises Group. And it's a pleasure to see such a large and engaged audience joining with us from various industries. And it seems that they are keen to know more about additive manufacturing. So I would like to express my sincere gratitude to OEM Update magazine, Phillips Additive, and EOS for providing me this an opportunity to share our experience in applying AM in die casting dies. So I would like to begin my presentation with a short introduction of my esteemed organization. Yeah, so in India,
Sorry,
actually, people know.
Sorry, you are sharing the wrong slide. There's also, can you put it in presentation mode?
1 second. Huh? Are you able to see
Sorry?
clearly now?
Sir, we can see. Yeah, now it's perfect, sir. Wonderful.
Okay, okay, sorry. Yeah. So in India, Godrej is the largest privately owned company, and we are existing since 127 years. And it is known for rich legacy of strong value system of Godrej, of integrity, trust, respect, customer centricity, entrepreneurship, and environmental stewardship. So tooling is one of the SBU of this large business house. Godrej is a multi-product and multi-industry sector leader, and we are working and we are serving a very diversified portfolio, serving B2C and B2B segment. And most of our SBUs, we have total 14 SBUs, and we are leaders in their respective areas. So coming to tooling, in tooling we serve automobile industry and majorly, and we also serve non-auto industry also. So we are offering solutions, complete solution to all the OEMs and their part producer by serving them through die casting dies, stamping tools, and industrial machines. And this is in brief about our product portfolio with respect to die casting dies. So we have a capacity to make more than 300 dies per year, and we are actually offering a lowest TCO to all our customers with superior build quality of dies and superior engineered dies. So, and we provide better value for money to all our customers till the end of life of the dies. So coming to the TCO concept, so we are a forward-looking organization and we seek to implement latest technology in all our products and processes. So we come across many relevant, irrelevant, or say feasible, unfeasible, and viable and unviable proposals, and pursue one that passes through our multiple lenses of strategic, futuristic, technical, and commercial evaluation. So today, in fact, we will discuss about the concept of TCO. So TCO, you are aware, but just to recap it shortly, it's an overall cost of products and service throughout its life cycle. So both direct and indirect costs need to be considered here. So it's a correct way of making decision when you are planning for buying any equipment. So I'm sure that everyone is aware about direct cost. With respect to die casting, it is a cost of the tool, and indirect cost, and those are hidden cost. That is because of the low yield, or because of higher scrap cost, or because of some part rejections, cost of field failure. All this adds to the cost which we are not calculating when we are planning to make any investment with respect to tooling. So to understand the concept in a simpler way, when we own a car, then with respect to TCO, then we should be looking at purchase price of the car, then cost incurred during its useful life. So that is the fuel used, then insurance charges, repairs, depreciation cost, plus parking toll, etc. And finally the remaining or resale value. So that is the total cost of ownership. In manufacturing industry, it is again initial cost of acquiring some equipment, then cost of operation, cost of maintenance, cost of downtime, cost of production, and then whatever scrap value is there. So from this actually we derive the total cost of ownership. And when we look through this lens, then we come to know that initially what proposal we thought that is a good, whether it is really good with respect to TCO, because first initially purchase price may look lucrative, but total cost, that is if we calculate the hidden cost, then it will be, we will come to know that it is not the best TCO, whatever decision we want to make. So in die casting dies, if we try to look at all the cost elements, so cost elements list is given here. So it starts with the tooling cost, then cost of casting rejection, then rejection at the machining stage, spares part cost, transportation, power consumption, and so on. So all these costs, there are cost contributing factors also, which we should be looking into detail, and then we will see that some of these cost elements or I would say most of the cost elements are having a negative impact on total cost of ownership. So we should be very careful about these type of cost elements which are going to affect the total cost of ownership. So here actually I shortlisted few elements where the cost contributing factors affecting majorly the total cost of ownership. So here these things are actually, if we go into detail one by one, then that indicates that mainly it is because of thermal management that costing rejection occurs. I think the casting rejection occurs as informed by Joe through some study by NADCA, that porosity is the major cause of rejection. And again, porosity is influenced by your thermal management, and besides many other things. But thermal management has a very important influence on the rejection of the castings. So if we try to understand like how the high pressure die casting operation happens, so in a shift, actually, if there are 150 parts are being produced on an average, so it goes through a thermal cycle of ranging from 150 degrees centigrade to around 520, or it sometimes it reaches 600 degrees centigrade, and the cycle time is hardly 150 seconds. So because of this huge temperature fluctuation, the condition of the die steel actually remains very challenging because it affects the yield strength of the tool steel. So this temperature gradient affects the life of the tool, and also the casting which comes out from this, that is also actually getting affected, because it when the tool steel comes in contact with a very high temperature of the aluminum material, then on surface the temperature increases, and on the core the temperature is not so much passed on. Because of this, there will be a compressive and tensile stresses in the same section of the die, and because of this it is affecting the die life. So as a tool maker, what we do is we understand the impact of thermal cycle on the each die element. So we design thermal circuit by taking help of empirical formulas and also validating through the simulation software. So if we go deeper into thermal system design, then there are 4 types of thermal system designs, and I will just take you briefly through that. One is very conventional line and spot cooling, where cooling holes are, I would say, temperature controlling holes are drilled, and those are straight holes, and hot oil is circulated or water is circulated to maintain the temperature. Whereas whenever there are thin round pins are there, so there we go for jet cooling, because normal cooling circuits will not be applicable here, and jet cooling holds in the range of say 3 to 4 millimeter, and in that we inject water and along with air, and then after that actually we try to control the temperature. There is another method called intermittent cooling. Here the cooling is started and stopped. So you can see the how the temperature is getting affected when the it is continuously cooled or not cooled, and against when the interval cooling is being used. We can see the difference in temperature of around 70 degrees centigrade. So this actually helps us to maintain the thermal profile of the die insert when the casting is being produced. The next is the conformal cooling. Now, in conformal cooling, as indicated by Joe and Michael, that here the 3D printing technology, that is additive manufacturing, is being used. Here, in this case, actually, we try to bring the cooling channels as close to the outer surface of the insert, so that very effectively cooling happens, and then actually we are able to maintain the required thermal profile of the part, so that any rejection due to shrinkage porosity and soldering, those things can be avoided. So conformal cooling, how it can be deployed. So now if you look at the advantages of 3D printing or additive manufacturing, so in tool making or in total industry, I would say part making industry. So first thing is not only the cooling cycle, but with respect to the complex geometry. So on the right hand side, the top one, it is one of the image of an insert where very thin projections are need to be finally achieved. Now those thin projection can be achieved either by machining, by using some EDM operation, which is again a very costly, and lot of material need to be removed from very narrow grooves. So your metal cutting time increases because of that. If we go with the 3D printing where the material is actually getting built, so you get advantage of very less machining and near net shape of actually profile can be generated by using additive manufacturing. Second is about internal cooling channels, which is the second image from the top on the right hand side. So very intricate cooling channels, which is depicted with green color. Now these type of cooling channels, otherwise it is not possible with any of the conventional method, can be achieved so that your thermal profile remains better. Next is about rapid prototyping. I think both the panelists have indicated and talked in depth about the rapid prototyping. And many times in die, any die elements, it breaks. Then to actually restore that, it takes a longer time for manufacturing a new insert. So immediately it can be built up by using additive manufacturing, and the portion which has been broken, it can be actually made by additive manufacturing at a very faster pace so that you can restart your production cycle as early as possible by using additive manufacturing. Now, I will be actually indicating about sharing our experience in applying additive manufacturing in a very in a high pressure die casting die. So in this die, actually, this is a problem case where the internal profile, the temperature was increasing to such an extent that scoring were observed. Now this profile, what we see here is yeah, so this profile is getting formed by a local insert. Now to this insert being so thin section, we are not able to provide any cooling lines over here up to the top of green area, which is highlighted here. And because of this, the temperature increases to such an extent that aluminum sticks to the tool steel and then soldering occurs. Now, because of this, many times casting gets stuck in the die, very difficult to remove, or aluminum material will remain in the die even the casting is ejected. Then it affects the surface finish of the casting, and many times casting production stops here. So because of this, lot of rejection occurs. And important thing is because of since there is no cooling channel here, the life of this insert is hardly 30,000 shots, whereas the normal die life goes up to 1 lakh shots or 1.25 lakh shots. So based on our simulation study, we have designed cooling system if we apply 3D printing technology here. So in this case, we have derived two type of circuits, and then effectiveness of these circuits has been verified. And we have seen that on the left hand side, this circuit is more effective. And because of this, then we have again gone ahead by making 3D printed insert with the type of cooling channels. What you can see here, this is an after the part is insert is 3D printed, we have done the X-ray to just to see whether cooling channels are in the right place, or it should not be very close to the surface that puncture may happen. So this is the machine which has been used for making this 3D printed insert. This is in after additive manufacturing. The piece looks like this, and after the final finish machining, it looks like this. So with this, actually, the insert has been made, and our story doesn't end here. Now we have to actually test it, like whatever we have seen in theory. Now how it actually, what type of benefit we get. So we have made a case study that when there is a regular insert which normally being used. So average temperature was 270 degrees centigrade in this area. whereas with 3D printed insert, it came down to 180 degrees centigrade. So because of this temperature difference, the soldering problem has been resolved because of good thermal efficiency here. So with the conventional method, this problem which I had indicated, and this is by using 3D printed insert, and then whatever advantage we got, that there was no scoring observed throughout the life of the punch, and the punch life has increased by 3 times. So it was lasting till the complete die life of the entire die. And of course, there is a cost attached to it. It is 2.5 times more than the regular piece what we would have made. But again, there is a minimum 8% increase in the production per shift. So you can calculate how much additional production has been produced by using this area, because all those disadvantages of soldering occurring and then doing regular polishing or getting the components rejected because of soldering, all those things are avoided. Cycle time has reduced, and also we are able to provide a good die casting die, trouble-free die casting die to our customers. So in a nutshell, I would say if we look at what are the advantages, so cost saving, as I indicated, even though the initial cost of investment appears more when I talked about TCO, but the running cost and the associated savings, if we calculated everything, then definitely this AM technology is a winner in die casting area. And also, another aspect we should be mindful of, that we are conserving natural resources and contributing to environment, because this is an example of 1 ton of H13 block. In a conventional way, now the rate would be in the range of 850 rupees per kg. We are removing around 400 kg of material just to get the profile. Now, that 400 kg of scrap actually will be selling at a 30 rupees per kg as a waste. Now, with additive manufacturing, what you make is what you want actually. What is the requirement? Only that much material will be built up, and only small allowances will be kept for finish machining. That's all. So you are conserving the natural resource of iron, also the energy which is required to remove so much of material from the solid block, and also you are generating, I would say, material for yourself also. With respect to cost also, this gives the advantage. So with respect to time, because the process is quite faster. So if you go for with conventional method, if you want to achieve some profile, and if you go with the 3D printing means, because the total lead time for making an insert by conventional method and by 3D printed method, there is advantage with respect to 50%. So that is one advantage. Then during operation, reduction in solidification time around 30%, and 5 to 10% reduction in die casting process cycle time. This is a great advantage to the foundry when they are using the tools which are made by using 3D printing. Another hidden advantages is production disruptions. All these can be avoided. Frequent polishing of the die insert, this also can be avoided. Die replacement, again, it's a big activity. We have to dismantle complete die if the core has failed, and then we have to in fact replace with the new core, and then validate it with respect to inspection and all. So all those things can be avoided. And important thing is reduction in production loss due to rejections. So rejection, actually, if it happens at casting stage, it has got certain cost. If rejection happens after the machining of the casting, then the rejection cost actually multiplies. And if it gets rejected at the field, then the cost of replacement and warranty claims and everything, that becomes an havoc for the OEM, for the part producer, and ultimately it comes to tool maker also. So this is the way we are seeing advantage in using 3D printing technology in die casting die manufacturing. Only thing we have to be mindful of, what are the pros and cons, what are the advantages we get by using this. It cannot be used in each and every area, but wherever we we are able to justify the initial investment and we see the benefit exceeding those kind of investment, then definitely we should be able to use this technology. So ultimately, once you actually invest in a 3D printed insert, and then recurring savings or recurring advantages can come to the die caster with respect to all these advantages. So this is what I just wanted to share with you. Thank you very much for your attention.
Thank you, Joyce, sir, for precisely covering the use of additive manufacturing in high-pressure die casting applications. We have poll questions ready for you. Also, if you have any questions for our panelists, please put them in Q&A box.
Okay, 46%, 48% participated. We are closing this poll right now. 49% participated. Thank you. Darshana, you can proceed.
Sure, sir. Thank you, panelists, for sharing your valuable insights on how tooling industry can witness a transformation with advanced additive manufacturing solutions. So to take up your questions, we have with us Mr. Samarth Deshpande, who is the application engineer at Phillips Machine Tools India Private Limited. Samarth, please take up the questions.
Thank you, Darshana. Thank you, panelists, for your experienced information, which has been enlightened with all our guests today. So let us take on the questions of for our guests. The first question would be to Joe, or any of the panelists who are free to answer. They can answer. So in die casting, which factor holds greater significance? Conformal cooling, cycle time, or the quality of produced parts? I think that was the polling question also from Jai sir at the last. So yeah, anyone from the panelist can answer. If they are willing to answer, can take up the question.
I'll go for this, and I mean from Jaysher as well as hands-on experience, deep hands-on experience, I would say. Thank you very much. So quality of parts comes number one for die casting, and cycle time comes number one for injection molding. So two different industries, two different priorities. Conformal cooling is the only solution that addresses both.
Thank you, Joe. Anyone else, if they want to elaborate on the question?
Yeah,
Okay.
so I would like to go. Like I 100% agree with what Joe has told. Especially in die casting, we are not very much mindful about cycle time because a lot of manual activity, especially I'm talking about Indian industry. So their part rejection, that is the most critical thing. And the conformal cooling helps us. We are not looking much at the cycle time and we are looking at the rejection percentage of what any tool can give. So I 100% agree with you. Thank you.
Thank you, Jayesh sir. Yes. So the next question would be how fusion between AM and parent steel is ensured. I think this would be regarding the hybrid print where our EOS machines are capable of doing with many materials such as MS1, H11, H13. I think Joe, you can take this question up and.
Yeah. So two different materials. Right, in terms of chemistry composition, two different materials, but if two different materials are processed right and then they have overlapping properties, right, or very similar properties, at least in terms of thermal characteristics, that they could bond well. But let's say we have the copper beryllium insert coming in and then we wanted to print it on steel platform. may not be so. The percentage elongations, the thermal characteristics of those materials are way different than steels. So we need to understand, or we need to at first see how these materials behave thermally, and then if they have overlapping properties, good to go.
The best example would be, I think, H11 and MS1 or H13 materials for the hybrid printing is what I have experienced with the overlapping properties, right? Um, so yeah, moving on. So the next question, how does a Gaussian beam differ from top hat beam in terms of application performance, and how does the beam shaping influence the quality of melt pool? Michael? Um
Thank you. I hope you can hear me now better than before. I realized it was the wrong microphone chosen. So my
Yes.
sincere apologies for this. I hope the subtext was correcting for it. Thank you for the question. So the different beam shapes have a significant influence on the application performance. Yes. We were very often asked the question, what mechanical properties can we achieve? Are they more like cast? Are they like forged? Are they like wrought material? The answer to that is, well, they are additive and they can be fine-tuned to your specific needs. With the tool of beam shaping, whether it's a top hat or a Gaussian profile or a donut profile or asymmetric beam shape, we see that we can create very new mechanical properties that have not been possible before, that were unknown to industries, and where we also can make parts out of materials that were not weldable before. So the question is very important and right, and it's you. You as customer, you have to decide, and you have to dictate us as the OEM what properties you need, and we can make them a reality. So the beam shape can influence the part properties very dramatically and significantly in a positive way, but also in a negative way. For some customers, speed is king, and they need the cheapest, fastest possible processes available. They don't care so much about the 99.999% dense material. They are okay with 99.5% density. They need performance. Others need superior properties. They need the least amount of pores to be polishable without hipping, or for an example. So with beam shaping, you have another tool that can make this a reality.
Okay, thank you, Michael. I hope the whoever has asked this question has got his answer perfectly. Um, so next question is from Gautam Mishra. Different AM technologies like DMLS, VAM, binder jetting, yes, offers varying material properties. How do you determine the optimal AM process and material for tooling applications, considering wear resistance, thermal fatigue? Joe, Michael, anyone?
Yeah, I can take it up. So different manufacturing processes, right? But same material, then we stick on to the standards, what the standards dictate. If it is so and so mechanical property that the standard says that we have to meet in, then whichever process that gives you the best properties at first, the quickest time, and the cheapest cost. And apart from that, if you have any geometrical constraints, yes, DMLS could work because we have the layer by layer powder bed coming in. So we have the design freedom. VAM might have little bottleneck with Y and T geometries. Binder jetting could have some shrinkages. DED, similar to VAM, could have the Y and T based geometries. So I would say if you have to rank, the number one will be DMLS, followed by binder jetting, followed by DED, and followed by VAM. So that's how we can rank in terms of capabilities. In terms of properties, DMLS for sure can address, and we have proved that our properties, the properties that we get out of DMLS after heat treatment stage meets the industry standards of tool steel. So there you have it.
So being a pioneer in DMLS systems, I think DMLS would be the most optimal process, right? Uh, Thank you, Joe.
Not just
Like,
that, actually, but because we are able to achieve the properties,
yes,
that's
that's the whole.
that makes the turning point.
Yes. Thank you, Joe. Yes. So next question is to Jayesh sir. How is AIM impacting the automotive and aerospace sectors that rely heavily on HPDC? I think that's the very good question for you, sir.
Yeah. So can you just repeat it? I think I just missed your word. Yeah, please.
How is additive manufacturing impacting the automotive and
Oh,
aerospace sectors that rely heavily on HPDC?
yeah. Yeah. So if you look at automotive, they always talk about huge numbers. And if you look at aerospace, yes, their requirement is almost 2 to 3% of what automotive is asking in terms of quantity. So we are looking at 3D printing technology as a complementing technology for say tool makers, because we use that technology for making tools, and those tools are used for making the mass produced parts. Okay, so for automobile industry, yes, it is like they have to go with that tool concept and then get the parts made. But for aerospace industry or for prototyping, because especially for prototyping, you need to have a few number of pieces to validate everything. With respect to strength, actually, I think Joe and Michael will be able to throw more light on that. Whether they will be able to do any functional testing with the 3D printed part in for automobile application. Say for engine block, if it is made by 3D printed, can it be used for actual testing or performance of the engine? So that I'm not very clear, but for aerospace industry, I think, and it is being used also for all the type of component by 3D printing. So as a tool maker, I would say I am looking that not as a threat, but as a complementing technology, which is helping me to reduce the rejections, development time, and also total cost of ownership. So yeah, so in a nutshell, we can say for aerospace, for automobile industry, additive manufacturing through tooling solution, and for aerospace, it may be directly 3D printed part to aerospace technology. Yeah.
Okay. Thank you, sir. Joe, any thoughts on this?
So has answered perfectly, because the cost of economics is different in automotive industry and it's different in aerospace. So rightly said, sir. I don't have anything to add. Yeah.
Thank you, Joe. Thank you, sir.
I might add just a
Sure.
little side note, because I thought there was a question from Jayesh. So can it be used in automotive testing? I think it's a very important question, because again, here you have to additively supply a part that has equivalent mechanical properties than your final aluminum die-cast part that you show. So if you have superior mechanical properties in additive manufactured, you did not win. If you have inferior properties, you again did not win. You have to provide a part with the exact right properties. And therefore, the interaction is very important between the end customer and his requirements and the OEM that manufactures the parts, that has the control over the process.
True.
Thank you.
True. Yeah, because we hear from market also that the end property is somewhere around 180 megapascals or so. If we deliver a part that goes about 250 megapascals, we lose the race. If we deliver about 100 megapascals, does not meet the requirement. If we have the right property in that range, then it makes sense. The delta has to be addressed. I agree.
Yeah. Thank you, Michael. Thank you, Joe. Next question is again for Jayesh, sir. What is preventing Godrej from printing the entire insert with conformal cooling advantages, especially given the higher printing build rates, thereby avoiding the sub inserts, which hampers the die life? I think they are already printing it.
Oh, yeah. So at the I think end of my presentation, I mentioned it that we have to look at really because currently the 3D printing technology is comparatively it is 2.5 times expensive than the normal manufacturing method. So we have to pick and choose like where what type of issues I will be encountering, and whether 3D printing is having a solution for that type of issue, and where I should be using it. I will be very happy to make the entire insert in the 3D printed, but ultimately the cost of tooling and everything need to be justified with respect to increase in die life and other things. So I think technology is evolving. In fact, every technology is evolving, but 3D printing technology is evolving very fast. And a day will come that it has been used so widely that total cost of operation will go on reducing it. And then it may directly compete with the conventional method of machining. So I'm looking for that day to come, and definitely I will be able to supply complete die made by 3D printing. Yes.
That would be great, sir. Yeah, that the evolution is really going is accelerated actually. Um, any other thoughts regarding this question, Michael or Joe? I think yeah, this is for Godrej, so Jay sir has answered perfectly. So let's move on. Can AM part be heat treated? If yes, what is the process? This is to question. This question is to Joe. Yes, the AM part can be heat treated, is what I can tell. Joe, if you can elaborate on this, that would be good.
Go ahead.
Yeah, you can elaborate on this answer.
So AM part soon after printing behaves just like any other part, any other rod part. You can heat treat it, you can nitrate it, depending on your requirement. You can do all sorts of post processing. You can do diamond polishing, if the tool requires, and so on. Yeah, there are enough number of technologies to take from near net shape to net shape and achieve the property. So thermal processing is a part of it, and AM products can undergo it. No issues about it.
And for the processes, you can always look into our data sheets, which is mentioned in our in EOS websites for whatever the material you require. Right. Next question is from Kuldeep Gora again. This is for Jay sir. Will there be any challenge in coolant flow in case of conformal cooling? I
Yeah.
think this question can be answered. Is
Yeah.
directed to all. Can be directed to all.
Correct. Correct. Yes. So the type of care we take when we are using jet cooling, now similar care need to be taken here, because the cooling channel size is very small, because ultimately it is to follow the intricate profile of the insert. So because of that, the size remains smaller, and then the normal water cannot be used here. And also the pressure, which is the line pressure, which is available, will not be sufficient to make the coolant flow through the entire cooling circuit. So in that case, along with the water, air, and the quality of water, scale free and all, what we care normally take with the jet cooling, same thing need to be taken here. So if Joe has got anything more to add, please go ahead. Yeah.
So you're right. I would say the three abstract rules that we have shared follow the profile of the part. Secondly, have don't have sharp edges or blind channels, but rather have smooth channels whereby you can avoid these scalings, where you can avoid pressure losses. Too many branches, not preferable, but limited branches, but with larger profiles could work. So those are definitely we have to follow the design rules. We can have the creativity, but as long as that is benefiting us, it makes sense. Otherwise, it's a fantastic demo piece.
Yeah. So even these design rules are under DFAM, that is designed for additive manufacturing, where not only for the tooling industry, but I think overall in AM, overall in 3D printing, there are some set of rules which can be followed, which should be followed um, to make this particular industry successful, right? Um, yeah. So next question by Sagar Tamane. How does EOS M4 support hybrid manufacturing AM plus CNC to produce high precision, ready to tooling components. Yes, Michael or Joe, anyone can take up this question.
So if I read the question right, it's about hybrid
M-
components.
For M4, yeah.
So in theory, as all of machines are capable to use 0-point clamping systems, so that you know exactly where, for instance, preform is being positioned within the process chamber. So it is known where the position of the part is. The precision of the machine itself is better than 50 microns. So 50 micrometers is the positioning tolerance, so to say, that you can achieve, but it can be also fine-tuned to be even better in certain requirements or parts can be made available. So you know where your part is. You can add on top of that part your AM component. You can take it out of the machine. You can position it in a CNC machining for final surface operations or whatever, and then have a finalized product, so to say, in the end. So it's both and all is possible.
Thank you, Michael. Yes, hybrid machining or hybrid printing is possible in all our portfolio machines, M290, M300, and M4. That it's just the process of manufacturing is a bit different here. Yeah, I think we are already over the time, so we can end the question and answer QA session. If you guys have any other questions to the panelist, you can ask them. You can connect them through LinkedIn or the email IDs. I think that will be posted in the chat or something. You can ask them any kind of questions and they will be able to answer it. Thank you.
Thank you, Samarth. And thank you everyone for being part of this lively discussion. We hope you have enjoyed the session thoroughly. Before wrapping up today's session, I would like to thank our speakers, Mr. Jayesh Kumar Rathod, Mr. Michael Jan Kalpa, Mr. Joe Ajay, and thank you, Samarth, for moderating the session. I would also like to extend thanks to Phillips Additive Manufacturing and EOS for taking this initiative and steering the conversation on additive manufacturing. We request our delegates and viewers to stay connected with us on our social media handles. OEM Update magazine is available on Facebook, Twitter, and Instagram. You can also download our apps from Google Play and App Store. With this, we want to end the closing of today's session. Please stay tuned for more such sessions. Thank you.
Thank you. See you. Bye-bye.
Yeah, thank you very much. It was nice virtually meeting you all. Thank you so much. Yeah, we'll be in touch
Yeah.
definitely. Yeah.
Thank you also.
Thank you.
Bye-bye.
Everyone. Thank you. Bye.